about another optimization technique, guys. Let's talk about another optimization technique. And this is not specific to C#. I will show you how to implement a C# version for this. But this is a general computer science optimization. And anyone out there who's taking computer science courses or has a degree in computer science, maybe you've had a class that talked about this or you've used this, and that's great. So I'm going to nuke all this code, guys. Don't worry. Don't worry, I'm just going to nuke it all. Most of it. I want to keep our measure, though. I want to keep our measure. I will put up on my GitHub. I will give you guys a project on my GitHub by the end of the stream that has that fast object allocator code. Any of the other utilities and extensions that we write today, we'll have up there. Don't worry about that. Just because I deleted it here, I still got it. Don't worry. You know, we still have a fast object allocator right there, right? Memoization, guys. Anybody out there? Does anyone out there know what memoization is? If it is, I would love to hear Stream tell me what memoization is. Let's hear it, guys. What is IOC, Massey? Inversion of control. Another term is I'm failing my words right now. Inversion of control, or DI, and all of a sudden I can't remember what the D stands for because it's 9 a.m. in the morning. Dependency injection, sorry. Woo! Inversion of control or dependency injection. They're almost interchangeable terms most of the time. And how we do in C# and .NET, how IOC is mostly done is via interfaces. And more reports to be coming to mind. Nice, nice. Expensive function calls and returning the cache result. Right? There we go, guys. I love it. I love it. Everybody's got the answer here. Let's do it. Now, Diego, are you saying my class new object equals my class, but your faster has better syntax? So, Diego, as we said, if you remember back when we wrote our code, my code, it's always better if you know at compile time, if you know the class type, use that in your object initialization. Just use that class type. If you know it at compile time, if you're writing the code for it, use that. If you don't know it, if it's coming from a generic, it's coming from a template, or if it's coming from reverse type or a lookup type or something like that, you can use my code. Why is it called .NET and .com? Whoa, Frog. Whoa. All right, guys, let's take a look at memoization, right? We'll create a little example, and then we'll see how we can easily memoize it, right? Man, I always fail at pronouncing that word. So I'm going to go back to my full screen just so we can focus here. Just so we can focus, guys, right? Memoization. Let's create, I have one already. I wrote one yesterday, just so we have something to test with. I'm going to pop it up here. Find prime number, right? I just want a function that takes an input, returns a unique output tied to that input, and the function call itself is expensive, right? So this technique should only be used in a couple of cases, right? Case number one, it takes input data. If you don't take input data, this has no use for you. It takes input data and does something with that input data. Hopefully it returns some output data, but it doesn't actually have to return output data for you to use this. It's more about the input data tied to the function execution. So that's use case one, input data. Number two, restriction. The function call cannot use any outside data for control flow or for computation, right? The function has to 100% only use your input data. Input data doesn't have to be just one variable. This can be as many variables as you want. Our case is just one. But as long as the function is only executing against that input data, you can use this technique. If it's executing against outside data, you cannot use this because you will get back invalid results, cached results, right? But that's okay. Even with those restrictions, there are a ton of use cases where this can help your software. Like finding a prime number as an example, right? Obviously, you can use your own lookup table and says, hey, I've already done this prime number lookup. Don't recall that function. But there's a lot of overhead. You got to go write this every time. You got to create all these crazy lookup tables. we can wrap this ourselves in .NET and make this easy, right? So while this is not as esoteric as what I just did with the IL, this is still a very valid case, and you'll probably use this more than you use my fast object allocator, just because, right? But we have a find prime number. Let's go write a measurement of this and just see how long it normally takes for some test data, right? So let's see, int reps, go back to 5, int it's 50,000, right? I don't know. Let's give it a nice large number to really measure some performance, right? And then we want to measure. We'll call this our baseline. Reps, right? This is an anonymous function again. And in our anonymous function, iterate through some reps. No, I'm sorry, not reps. What I'm talking about, iterate through our iterations. I had to fix myself there for a second. And what are we going to do in here? We're just going to go find prime number. And I'm just going to give it some number, right? Let's go find prime for 45. That's fine. Just want to throw something in there. Let's let it run. All right, let's see how long this takes. Let's see what our baseline takes. And we are in release mode. Always important to make sure when you're measuring performance. How long is this going to take? Will this take too long? No, not too long. On average, 376 milliseconds, right? And let's run that again. Make sure we're staying consistent. 376, 74 milliseconds. Excellent, excellent stuff. All right, how can we go memoize this? How can we say, okay, well, this is taking 45. We're always going to get back the same output data. We don't need to call this every time. How can we go fix this? How can we go make this better? Let's go add a new class to wrap this. Let's see if I can spell correctly. Let's call it Memoization. And this will be that's fine, public static class, something what I want to call this, utils. Because this is going to be a static method. You can even make this an extension method off of something if you want. All types of crazy stuff if you want. But really, this is a very simple implementation I'm going to do right here. Public static func that takes in an argument. That takes an arg. Has a return value. So this is, we're going to memoize functions that can use one argument. If you want to expand this out to multiples, you can do that, right? But for our use case here on stream, one argument with a return type, right? Of arg. Oops, sorry. Of arg and ret, right? Oh, you know, I'm thinking if I want to make this an extension method. I am going to make this an extension method. Yeah, let's just do that. So this is, if you've never done an extension method before, guys, this is how we're going to do an extension method. So we are going to extend any func of this template type. Yes, you can do extension methods off specific types, right? So any func that takes one argument and one return value, we will have a memoize function around it, right? I'm going to call this our functor. So there's our function. We got to go build this now. How a memoization works, right? We need some type of ledger. We need some type of lookup table for input to output data. So we can go create that. And why am I putting this in our extension? Isn't this going to get called every time? Well, it's not, and I'll show you why. So we're just going to use some basic .NET types, right? You can optimize this however you want when you get around to it. So we're going to take in a dictionary, again, of arg and ret. Right? So we want to look up an argument, value, and to its return value. Very simple, right? We just want to create a new dictionary. But you'd think every time this gets called, we're going to get a new dictionary. Well, yes, every time this gets called, we get a new dictionary. But this is not our function. Because, see, this returns a function, right? We're going to memoize a function. We're going to return a new function. I'm going to create a new dictionary for that. What are we going to return then? Return, and I'm going to create this as a lambda just because we're cool like that. I'm going to return, we're going to call it arg0, right? So this is our I'll make it a little easier for you guys, because I was about to type this in an optimized fashion, and I shouldn't do that. So what are we doing? We have a return value, right? Here's our func return value. And then how all memoization basically works, we just check our lookup table, try get value. And why are we using a try get value? Why aren't we saying that contains and then lookup, right? Try get value is if you don't know around dictionaries, right? This is not very advanced, but always use try get values if you can, guys. If you use a dictionary and you want to say, hey, if this contains, return our value, otherwise do something else. Try get value will do that contains for you and give you back the value at the same time and return a bool, true or false, if it contained it or not, right? So arg0 is our input parameter, right? Because this is a lambda. We're creating a lambda around arg0, which is going to get passed in. You'll see what I mean when this is done. And if this returns an out of func return value, right? So if this did not contain it, if this was not in our dictionary, that means we've never run this function against this argument value. We want to just go do the slow function call of arg0, right? So here is our memoization function. We're going to wrap this function, functor. Here we need to go call it with this argument that's going to get passed in, get back our value, and a memotable.add of arg0 of func return value, right? Just go create a lookup of this. Go store it in our memoization table. And that's really all I have to do there, because down here we're just going to return the func return value. So this, if it's not there, go add it. Go store it in a local variable, right? But go add it. If it is there, this will never get called. We don't have to recall the function if we already have this input value cached. And then we want to go and return our func return value, right? And there we go, right? So now this is a lambda. So what are we building here? What are we building? We're building a lambda anonymous function. That's what this is. Then we're going to return it because this anonymous function can map to a funct of arg return, right? Because this has the this has our return value of ret, right? Ret return value. So the lambda knows what's up. It has an argument which we pass in as arg0. So we're going to get back a funct of arg0. That's what we're going to return from our memoization. Our dictionary here, since we created outside of the lambda of the anonymous function, this is created just once. The instance of this is now tied into this anonymous function. So as long as this anonymous function exists, this table will exist, and they'll get cleaned up together, right? So we don't have to do any type of weird storage of this dictionary. It's going to get tied to this funct object, right? Great thing about anonymous functions, it'll allow you to tie data together that you don't have to go build yourself. So there we go, guys. We have ourselves a memoization function. Let me go fix what I have. Oh, public static, right? If we're using an extension method, make sure it's a static. So remember, we're extending funct of this, right? Right. Well, then, we have it. How about we try and go measure it now? Baseline memo. So what we want to do before we measure, how you memoize a function with how we did this, we need to do that, right? So we want to do a var memfunc is based on our find prime numbers. Let me see if I did this right. Am I thinking about this right? Based around our funct of this, right? A funct of arguments, int long. Should have, let me see if I have this in here. If we did this the right way, because well, we can always call it like this as well, right? Utils memoize of our int in long. We pass in find prime number. I'm not sure why it's not passing it on here, because normally we should be able to do memfunc find prime number of memoize. I'm thinking of that wrong, but that's okay. This will work as well. We'll have our memfunc. So this is going to memoize our find prime number function, right? And instead of calling find prime number, we just call our delegate, our funct, for our memoization, right? So now if we run this, and we'll let this execute, without any surprise, by the way, we get a huge, huge performance boost because we're only passing in one static number, right? We're passing in one static number. Let's close that down. So our baseline is, our average is going to be the same time it takes to run it every time. Whereas in our memo, this is, since we're only passing it in one time, we only have to execute our function one time, and this is going to do a dictionary lookup, which is very fast. So every time we run this function after the first time, which by the way is our warm-up method. If you notice if you remember in our measure, we don't time our warm-up action. This warm-up action is warming up that dictionary as well and storing it in there one time, right? We're going to get it stored in there one time, and that's why we don't have a max of 300. Because it's already been warmed up, so every time we call it now, it's the memoized version. It already has that cached in there. We could solve this, of course, in our measure by passing in some random data, which would show us that our average would go up, of course, every time we call it the first time with new data. It's going to have to execute our function, and it'll be cached. So here's one way you can memoize stuff. Right now, some words of caution around our memoization. This is not thread safe. Remember, we're using a dictionary, and this is not thread safe at all. We can make this thread safe by using a concurrent dictionary. If I can type correctly. I'll get chat in a second, by the way. So if we use a concurrent dictionary, we need to do a triad. Yep, and now we've just made this thread safe for the most part by making a concurrent dictionary. This is going to slow our performance down ever so slightly, but not really a noticeable measurement, right? Not really a noticeable measurement when we make this a concurrent dictionary. But now that it's a concurrent dictionary, it's thread safe. You can have multiple threads calling into this delegate or this static func. And the dictionary will be thread safe around, and that's the part that was not thread safe. Let me go pull up my screen here and see what's going on in chat. See if anything interesting is being said. So, any questions on this, guys, that I can answer about memoization? This is not a specific C# optimization. This is a general computer science optimization. That we use a lot of times. You got to be careful we use it though, guys, right? Only memoized functions. We already talked about restrictions, right? One, need to be a member variable. Oh, why does it need to be a member variable? This is not, remember guys, we're creating a static function. All we're returning here is a lambda. We're returning an anonymous function here, right? So since we're returning an anonymous function, we're creating a dictionary outside the function, but since we're using the dictionary inside the anonymous function, .NET C#, when it compiles this, is going to move this reference table into here, right? It's not going to create it out here. It's just going to say, hey, I have a reference to this, and because of how .NET works and how garbage collection works, since memtable has a reference in this function, garbage collection will not delete this. Would this speed up lookups to a huge dictionary? Yes, Jim. Well, no, Jim, no, Jim, it would not. If the lookups in the dictionary is same as a normal dictionary, you would get the same speed, right? Because this is, Jim, right? This is just a lookup into a potentially huge dictionary. You want me to do a step-by-step debug? Absolutely. Let's go to debug mode. Let's step through this in the debugger. I like that idea. We'll put a breakpoint up here, and we'll put a breakpoint inside the function call, right? And then on top of that, we will do a breakpoint right here. When we're going to call this, right? This is the dark theme. Why not create the object inside the lambda? Zufi, I will tell you exactly why we don't want to create the object inside the lambda when I step through this. This is the dark theme with some custom color modifications. Yes. So let's run this, guys. Let's run this in debug mode, and let's see what's going on. So we have not hit our lambda yet, right? We're calling our memoization. If you look at our call stack, we're at our main, right? This is here. This is when we're creating the memoize function. You don't want to call this every time. You want to call this once to create the memoize version of your expensive function, and then you want to use this instead of the expensive function, right? So the first time we call this, we are going to create our memo table. So now we have a new dictionary. Excellent. And we're not going to call this function, right? This is just going to create the lambda. This is going to create the anonymous function. It's not going to execute it. This is not going to get executed. It's just going to get created. No problemo. We love that. And so nothing's happening. All we've done so far is create a dictionary, and we created an anonymous method. That's all that we've done so far, right? Now when we jump into here, when we want to go execute our lambda, this is the lambda we created. This is what got returned from the memoize. It's that lambda. If we step into the lambda, we're now inside the lambda, and this is why we don't want to create this dictionary inside the lambda, because if we did that, every time we called this function, we would end up recreating this dictionary, very expensive, and also we would lose our table, right? We create it once outside the lambda, and now we're just referencing it here, right? We know what memo table is, because the lambda builds it in as a local variable, as a reference, and it won't delete it because of that. Garbage collection won't delete it because there's a reference to it. Islinator, no reason. I'm just typing code quickly. No reason. You should probably give this a capital U. Yep, absolutely. So if we execute through this, right, we're going to step through this. We're going to look at our memo table. We're going to see that there's nothing in the memo table, right? So when this try get calls, it's going to fail because there's no return. There's no lookup to arg0 of 45, right, in our memo table. So we're going to have to go and execute our find prime number, our functor that got passed in. Let's step into that. And you can see it's just calling our find prime number. We're not going to run that because that's going to take a while. And then the return value of that's 197, right? That's our return value based on argument 45. And we want to go add that into our memo table now. So now we have a lookup. Now we have a lookup of 45 to 197, right? And then we're just going to return that. So there we go. Next time we execute this function, we step back in. We still have our memo table, right? Because it was created outside the lambda. We're just referencing it. It's created once. Now we're just using it. And now it has this lookup of arg45. And we're not going to step into here because our get value returns true. And we have the function value, right? That's all we're doing, guys. Very, very, very simple memoization, but it's just an easy way for us to wrap it.